Hi everyone. Please give a round of applause to our next speaker, Eric Chiang. Thank you all for participating in this presentation on insecurity protocols and overview of modern authentication. So if you have any questions, please put them in the Slido. All you have to do is either access the QR code that was outside of the theater, or you can go BSidesSF.org/Q&A and put your questions there, especially the support group out front. So let's get started.
All right. You can hear me? Yeah, cool. And yeah, there are way too many slides in this deck for questions. So if you do have questions, just find me at the bar after this talk, and I'm happy to complain to you in person. Welcome to the talk, Insecurity Protocols, an overview of modern authentication. I'm Eric. I work at Google. I work on things that aren't really related to authentication, but have in the past done stuff like device identity. I maintain a lot of really random open source projects. So if you see me on the internet, say hi. I promise and apologize if I've been mean to you over there. And then in the past, I've done things like I was the co-lead for the auth special interest group in Kubernetes. So we'll say that I'm qualified to give this talk. So today's talk is just kind of a whirlwind of modern authentication and some not so modern authentication. We'll get into that. So we're basically just going to go through a bunch of these protocols and things, and I'm going to say witty stuff, and that's basically the talk. So I don't know if there's an overarching theme, but hopefully that sounds interesting to all of you and the people in the overflow room for some reason. But hello, everybody. Buckle up. So just to dive into everyone's favorite sort of authentication scheme, JSON Web Tokens. You've probably heard of these, and if you haven't, behold, a JSON Web Token, a JWT. JWTs are a bunch of base64 information, but it uses a special base64 that's web native. And it has basically three parts. So a JSON Web Token is three pieces of information sort of shoved together. So the first part is a header. This holds metadata about the JWT. So, what algorithm was used to sign it and so on and so forth. The payload is a real meat and potatoes. This has information like what is the identity that this JWT represents, but people just shove random things in there. So like this admin key might be a good example. And then there's a signature, right? So the signature is just a cryptographic signature over the first two parts. So you take the first two parts, you put them together, and then you verify them against the signature. Nothing too crazy. JWTs are weirdly not the specification for the signature protocol. That's JWS. Yeah, just bear with us. JWTs are actually a specification of what's in the payload. So these are just claims like things you would expect. Who created this token? What does this token represent? When does this token expire? Nothing too crazy here. So yeah. A JWT is just a signature over some JSON data. Like, how bad could that be? But if you hang out with people at BSides, which I assume you do, you might have heard just like a general sense of security engineers grumbling about how awful JWTs are. And you might be wondering, like, where does that come from and what does that mean? So I think that this started about a decade ago with this one particular blog post by auth0. So this is a critical vulnerability in a few JSON Web Token libraries. I think this was like 4 or 5. So it's not even just like 1 or 2. It was a significant portion of the ecosystem. And the vulnerability that this blog post discussed was the fact that the way people were doing validation was that they were looking at the header, seeing the algorithm, and then using that to verify the signature, which on first glance might seem reasonable, but at that point, you haven't verified the signature yet, so you can just replace stuff in the algorithm. Specifically, you can use this one funny value. One hack to kind of get around all of these validations was just to use the none value, and then suddenly all of these libraries would just let you go forward, right? Like the none value means you don't have to verify the signature, so you don't. And I think that the JWT, reputation never really recovered from this particular moment, right? Which is maybe fair. This is pretty bad. There's actually a really funny website, which is how many days since the last JWT alg none vol. I think it was at like 200 or something. So we're all as an industry getting better, and I'm proud of us. More recent sort of research into why JWTs are bad are more focused on the fact that JWTs, it's a really quick explanation, and therefore they feel very accessible. And people do stuff like implement their own RSA padding. Just a reminder, JWTs are still cryptography, and you still have to treat them that way. And then, as I might have specified, JWTs are part of a much broader ecosystem. There's JWEs for symmetric encryption of a JSON object. There's weird things like multiple signature schemes for JWTs. Just throw those out if you ever see them in the wild. And then there's like certs and headers. So there's some just wild stuff that you can do as part of this. And then the thing that somebody has probably screamed at you at some point is don't use JWTs for sessions. I think that this actually doesn't necessarily correspond to JWTs, but is part of a broader conversation about how we want to represent sessions. Specifically, should sessions be stateful or stateless? A JWT is, quote unquote, stateless. You sign an object, you give it to a user, they go use it and come back. But there's not really a good way to revoke that session, right? You just have to wait for it to expire, or maybe you have some revocation process. That sounds awful for JWTs. So, the reality is that regardless of even if JWTs don't just sign documents, you want to be able to track sessions, you want to be able to log people out, for example. And I admit that I am totally guilty of this. I once regrettably in the past shoved some group information into a JWT. Definitely don't do that. It turns out if you remove somebody in a group, you don't want to have to wait for them to get another JWT for that to take effect, for example. So yeah, summary, I think that JWTs kind of get a bad rap. If you are ever going to use them, use a robust JWT library. There's plenty of successful JWT uses in the wild. We're going to go over a couple of these in the other slides, but things like Let's Encrypt, Acme use them. And, overall, I think the main reason that people don't like JWTs is because JWTs are often the wrong level of abstraction. JWTs aren't PKI infrastructure. They aren't like a security scheme. They're just a signed document. And I hit this a lot at work. Somebody will show up to me and be like, hi, I want to decrypt a secret with a TPM. Is that secure? And you're like, okay, can we take a step back and talk about what you're trying to do? And I feel like that's a lot of what people end up using JWTs for. On to the next protocol. So OAuth 2, you've maybe heard of this. OAuth 2 is the login with Google or login with X kind of thing that you see on the internet. And just to go over all of this with you, so let's say that I run a third-party server and I want to log in somebody with OAuth 2. So let's say I want to log in Tom over here. So Tom comes to my server. The first thing my server does is it kicks Tom over to the identity provider that I want to log into. So it just redirects them. And it redirects them with two kind of important pieces of information, even though there's lots of it. It has the app, right, like my third-party server, and it has the access, the information I'm trying to access from Tom's account. So this could be something as mundane as what is Tom's username? It could also be like, hi, Tom, I would like to manage all of your contacts or all of your drive data. That's a little bit more extreme. But if we get the approval from Tom that this is okay to let me access all his drive data, the identity provider will redirect back to my app, and it has some information, but the important thing is this code here. So that code is then something that I can exchange on the back end through my app with the identity provider. I provide it my client ID, my secret, my credentials, and then I get an access token. And that access token can be used to access anything that Tom has given me access to. So again, I can now go mess with his drive data. For considerations around OAuth 2, because this is a security conference, I glossed over this, but there's this thing called the state. States are funny because they're used to protect really weird attacks, like there's odd things that you can do to try to trick somebody to log into as your account. And if you don't have some sort of random value that you then compare against later on the flow, you can be susceptible to these type of things. A really big part of OAuth 2 as well is when you don't have a server. So a good example of this is a single page app. Like let's say you have a CDN and you have a bunch of React and you're serving a single page app. Or if you have a native app, so let's say I have an app on my phone. In those scenarios, you actually can't protect a client secret. There's no way for me to ship you an app without you being able to look at it, unfortunately. So more recent developments in OAuth 2 have been using this thing called PKCSE. I've heard this described as PIXE, so I'm just going to call it that, but please someone tell me if that's wrong. And the basic idea is that there's some hashing challenges, but it basically allows you to take the initial, tie the initial authentication request with the auth code exchange. And this protects against some weird things like somebody stealing your redirect URL and getting the code, and it blocks that. And what a cool outcome is you might have heard of the implicit flow. You don't have to worry about that anymore. The implicit flow has been dead for a while now, and it's kind of nice because you just get to use OAuth. Quick reminder of OAuth. Access tokens are still really, really dangerous. This was in March of this year. There was a startup that was like, manage your GitHub things or scrape it, but the account credential that it got also allowed it to like upload code to your repos. They had a breach. People's code got wrecked, I assume. And that's why if you're ever like in an enterprise setting, you're gonna see your enterprise sort of administrator really restricting what kind of scopes particular apps can request. And this is just a funny one from way back in the day. Like, you do have to consider the fact of what if somebody, creates an OAuth client called Google Drive and has their logo be the Google Drive logo. This is, more amusing than anything, and people have locked down. But if you're going to write your own OAuth 2 provider, you definitely have to consider this. And this is just like, in general, about not necessarily about OAuth 2, but about all the specs we're going to talk about. There's always just a ton of additional specs that exist out there. OAuth 2, we talked about PKCSE, like that's a really well-established way of using OAuth, but I've never heard of SAML assertions in OAuth 2, and that sounds awful. So for example, I think the main thing that you want to take away from the slide is like, just because there's an RFC does not mean it's a good idea. It turns out they don't really just like let anyone write RFCs, but like they kind of do. So yeah, summary of OAuth 2, it's totally ubiquitous. It actually has had some really cool improvements over this, like reducing the implicit flow and sticking to that kind of stuff, and access code's still stuck. There's not really a good way of doing that. Cool. OpenID Connect. The one problem with OAuth 2 is if I want to do basic things like get your username or your email, every freaking provider implements a different way of doing this. So this is on the top left is Facebook, then we have Microsoft, then we have some website called Twitter, and then finally GitHub. And all of these use different URLs, different paths, and like even if you're using a centralized spec like OAuth 2, you can't actually get people's information in a spec agnostic way. You have to know what provider you're talking to. So OpenID Connect is a way of basically avoiding all of that. Instead of there being sort of explicit or spec-specific kind of ways to get certain pieces of information, it defines a standard on top of OAuth 2 that allows you to get things like your email or your password, or not password, your profile name. So this includes a standard set of scopes to request, standard response fields, and some discovery information. So when you go through an OAuth dance with OpenID Connect enabled, as part of your token response, you'll get this thing. And if you were paying attention earlier on the slide, you might know what the ID token is, right? It's a JWT. So that JWT has different information depending on what scopes you've requested. So the OpenID scope is the thing that basically says, I'm using OpenID, OpenID Connect, excuse me, and it'll give you like a unique identifier for the user in the claims of that JWT that you've been passed. Profile gets you the name, preferred username, picture, and lots of other things, and then the email scope gets you email and if the email is verified or not. I don't know why you would ever not have a verified email, but whatever. And then just as a nice quality of life improvement, OpenID Connect has a discovery mechanism that you can give it one URL and then you can get all the other information about that provider. OpenID Connect, I think, while it is a really good spec-agnostic way, there are some weird nuances with different providers. So this is a blog post by Truffle Security, who I think has a few talks here today. But what they identified is that for Google, there's actually some weird edge cases where you can create non-Gmail accounts at like the foo.com with an @foo.com email. That actually does not imply that you are part of the foo.com organization. And if you were to like get the email, lop off the front bit and do the you might actually be allowing people to access your resources that are not part of your organization. And what this kind of implicitly means is that even though OpenID Connect is like this sort of agnostic thing, there are really annoying subtleties where you do have to actually end up being provider specific. Also, when you just give people JWTs, they happen to use them, which is another annoying part about JWTs. So people happen to use the JWT that's returned outside of all of the OAuth flows as authentication mechanisms. So Databricks, HashiCorp Vault, Kubernetes, these all will accept ID tokens as part of authentication. And in the OpenID Connect and OAuth flow, you're using TLS, so you don't actually technically need to verify the JWT. Here, you absolutely do. And that's when it gets nuanced and weird. There's things like providers that run multiple issues on the same infrastructure. You have to consider the fact that you want to allow some client IDs, but not others. And then people start getting clever with this kind of stuff where they allow you to request client IDs on behalf of other ones. So this is definitely something to watch out for. So yeah, OpenID Connect, summary, it's a standard on OAuth 2. There are still IDP-specific nuances, and yeah, you will see people just throwing ID tokens around totally outside of the scope of getting the user's email. And now my favorite, SAML. So I think JWTs like SAML, or SAML like JWTs, I think get a lot of flack from the internet, but I don't feel that SAML gets enough. So I'm going to basically go through a few slides about why I hate SAML. Okay, so SAML has a lot of different ways in which you can they're called bindings, the way that you can use it, but we're just going to focus on the OAuth-like bindings. So it's a really similar setup. I have a third-party server. I would like to authenticate a user through an identity provider. You happen to use a post rather than a redirect, but it's the same sort of thing, right? I want to log this person in. Rather than a three-letter grid flow, though, SAML just immediately posts some information back to you. So this is a SAML response that gets posted back to you, so you kind of just have to accept post requests from random places on the internet. And it includes a signed XML document with assertions describing information about the user and other fields describing information about who signed it. So you're like, okay, I have to validate a SAML signature. How hard could that be? This is a SAML signature. This is a lot, but I think the first thing I will call out is that the signature is inside the signed object, which doesn't make sense, okay? So the way that you would validate this document is you would pull out the signature, run XML canonicalization on the object you're trying to validate, and then validate it on the signature. Okay. Unfortunately, XML canonicalization is super complicated. This is an example from the spec, and if you read it closely, you'll notice it's reading a file called world.txt from disk and embedding it in the XML document. And I'm not saying that every XML parser will do this, but this is the kind of stuff when you're trying to implement things and read through a spec, you have to know, wait, does anyone actually do that? So there's tons of weird ways in which XML canonicalization is complicated. XML namespaces are insane. It's not as bad. It's not just simply oh, this is an element and this is its namespace, because namespaces are inherited. You can alias namespaces. There are default namespaces that are implicit. Attributes can have namespaces, and SAML absolutely uses all of this, so you have to be aware of it. And then finally, for some reason, you can not just sign the entire response. You're allowed to sign sub-portions of the document. So you can get a SAML response that is not signed, but it is totally valid because specific assertions are individually signed, which, again, is insane. So trying to just be a little bit subjective, every SAML implementation I've ever worked with has had an auth bypass, which that's not okay, right? If you will notice, I am on this list right above a CVEs 10. So yeah, we'll kind of conclude this talk or this particular session where it was. I think in general summary, I really like this quote, which is that, SAML is by far the worst commonly used industry cryptographic protocol. Again, I am kind of surprised that we just put SAML and OAuth 2 kind of in the same categories when one is clearly just completely insane and the other one is, I think, quite reasonable. Okay, palette cleanser. We're going to do FIDO2. So I've used security keys for a long time, 8 or 10 years or something like that. And I think anyone who else uses security keys, you'll probably have the general sense that, okay, it's a second factor and there's probably some cryptography going on underneath. So FIDO2 is two primary protocols, WebAuthn, which is the JavaScript API that browsers use to talk to your security key, and CTAP2, which is the way that your browser communicates with their security key. There are two phases as opposed to, some crazy number of APIs. So there's just, hey, I would like to register this key, and then I would later on like to authenticate it. So this is the registration phase. There is a challenge in here. This is mostly used to avoid replay attacks. So the key doesn't actually sign it. But effectively what it gets back from here is it's just a public key, and it has an ID. So really quite simple. And then when you want to challenge that, that public key or the security key, you give it an actual challenge to sign, as well as the ID of the key that you previously got from the last step. So hi, I have this key registered on me, on your account. Please sign this challenge, and if it signs it back, you're all good. And then under the hood, CTAP2 is using this thing called get assertion. CTAP2 is not, I think, a general signing API. You can't use it, for example, to drive like a TLS handshake or something like that. It signs a structure that includes information about that. There's actually some fun hacks in OpenSSH that allow you to use that when negotiating a protocol, and that's how SSH security key works. And a really cool, interesting part about that credential ID is that for a majority of security keys, this is actually an encrypted blob that includes your private key. So when you try to register a new key, the security key will generate a public-private key. It will encrypt the private part with a per-device encryption key and then hand it over. And what's really cool about that is that your security key actually doesn't need to hold any state. So you have these cool applied cryptography mechanisms where you have a security key that only has maybe one or two keys on it, but it can scale to allow you to log into a basically unlimited number of websites. So yeah, I think FIDO2 easily one of the best examples of actual modern authentication. And you can reason about the FIDO2 protocol, right? You can read the spec and it's not like super crazy. So yeah, I think it's probably one of my favorite uses of applied cryptography. And now we're going to talk about Passkeys. So Passkeys, basically like a product manager took a bong hit and was like, what if we took these security hardware keys but put them in software? And that's a passkey. So a passkey is, instead of being tied to a physical hardware token that is plugged into your laptop, it is this ephemeral thing that effectively can be synced between devices. So instead of it being this one thing here, it's on my phone, it's on my laptop, and it's just all kind of magical. Passkeys are intended as rather than as a second factor to replace the first factor. So passkeys are used as passwords rather than as an addition to your password, right? It is effectively like a password that you can't see. It uses the exact same protocol, but there are some nuances here. Namely, when your browser wants to challenge a passkey, it does not provide the client ID. So instead, you get this nice sort of user experience on your side, where instead of saying, please touch this security key that might be on the other device, your browser pops up a dialog that says, hi, someone would like to have challenge your passkey. Here's a set of passwords or passkeys that we have registered for this domain. What do you want to do? Unfortunately, passkeys or security keys turn out to make really bad passkeys. And this sort of, I would say, in a way that surprised me, at least, when I was doing research for this. So first off, security keys are hard because I have 5 or 6 security keys, right? And whenever I get a new one, I back it up for the few accounts that I really use security keys for. But this just doesn't really work if I am using them to store my passwords, right? I'm going to be over there. Oh wait, was it that security key that had the thing? And then, just in a really big, architectural issue, remember how I kind of talked about how the client ID stores and allows the security key to be stateless? Removing that means that the security key has to store that information. So it's this thing called a resident key. And basically, for stuff like YubiKeys, a lot of the generations only allowed you to store 24 keys, which is absolutely unacceptable. And what's even crazier is that many of those don't provide management interfaces for that. So as soon as you hit 24, you're out of passkeys. Also, passkeys are great, but there are really practical things that are annoying. So for example, I have a MacBook and I want Chrome to store this in a way that syncs to my Android phone. And it turns out there's not really a way, because Chrome happens to use iCloud Keychain, which can't back up to this. So practically, like, it's just really hard to get something that magically syncs between devices when, your phone won't talk to your laptop. So yeah, there are luckily flows that do this, but I was quite annoyed with this particular thing on the left because like 3 of these options basically mean either store it in a cloud provider I don't use or store it locally so you can never recover it. And I think for me, like Passkeys, like I'm a relative expert in this kind of stuff, and even I find this UX really confusing sometimes. So yeah, Passkeys, they're actually just a very small tweak on top of FIDO2, but it comes with huge user experience changes. And I think we can all agree, like, the interoperability issues are a really blocker if you don't happen to be part of one ecosystem. I have 5 minutes, so this is going to be fun. So I would love to talk a lot more about hardware auth and have other examples, but we're going to have to use the trusted platform module as sort of our stand-in for all the other ones. So trusted platform modules provide a few capabilities, and when I talk about trusted platform modules, you might think of this as like, what hardware auth in general tries to provide. So you can link keys to devices, you can attempt to attest the state of a particular device. So this would be, what did this operating system, did this boot with? What were the secure boot keys? And then additionally, you can guard secrets based on that state. These are all the commands from the TPM 2.0 spec. So again, 4 minutes, there's no way I'm actually going to give you a complete overview of how TPMs work. But generally, TPMs can store keys. So TPMs have many different kinds of keys, and these have different roles and responsibilities. Some might be used to sign assertions about the TPM, some might be used to encrypt or decrypt, and some might be used by applications. But the core thing is, as soon as you can prove that one key is on a TPM, it can attest to the fact that any other ones are. So if you know that a key is on the TPM, you can then create other keys that are provably also bound to that TPM and backed in hardware. And then it also has mechanisms for tracking state. So TPMs have these rolling hashes called PCRs, and then another thing that's outside of the TPM called the event log. The event log has a set of boot events. Again, this might be the hash of your initramfs or the actual secure boot certificates that were used to validate your operating system. And then if you want to add a new event, you append it to the event log, and then you roll the TPM hash forward, and there's no way to go back. And then later on, what you can do is you can challenge the TPM and say, hey, I know you have that key. Please sign the current state of your PCRs. You grab that attestation, you can then replay the event log and verify, okay, what I'm looking at is actually the state of my device, and you can do that remotely. There are lots of ways that this can go wrong. I had some fun with some coworkers once who wrote some code, and I was like, wait, you're relying on a field that isn't part of that digest. So again, TPMs are very complicated. It's hard to do this stuff. If you ever do feel like looking at the event log, please reach out to me, because there are actually very few vendors that seem to do this, and we have a lot of experience of trying to get the value of particular PCRs from vendors and just not really seeing it, for example. But yeah, do reach out. So yeah, TPMs are incredibly complex. I see I'm at 2 minutes. There's no way we're going to explain it all. But I think, in general, this kind of hardware attestation is incredibly commonplace. So you might be able to do things like FIDO has space for attestation. So you can, when you do a registration of a security key, you can say oh, is this in the batch of security keys that my company purchased? This is also used for anti-spam measures, right? If you want to know that, hey, is this application installed on a real Android device? You might not be getting the exact primitives that the operating system is linking into, but somewhere under the hood, something like this doesn't happen. And then finally, is this key backed by hardware? Again, security keys, have these kind of attestation capabilities, and in certain environments, this is absolutely required. Okay, in summary. So we just talked about, 6 or 7 kind of authentication protocols that are widely used. Again, I joke, but it's some of this is just going to be me up here complaining to you, all the audience, and I hope that was interesting. But I think, broadly speaking, what is very, very common is that things that we kind of think are similar are actually have huge differences in complexity. If you think about the FIDO2 API versus the TPM1 or OpenID Connect between SAML. And when you look at how complex something is, it is usually a good predictor for like how many CVEs are going to be against it, or how effectively insecure, or how much is Eric going to complain against it in its next slides. So I hope that was interesting. The slides are on my website, and thank you.
So if you enjoyed Eric's venting, please give him a second round of applause.